Okay. So let's start our third lecture by reviewing what we did in lecture 2. So in the second lecture, we found these scattering equations. And these were equations that connected the space of kinematic invariance I think I got a little tangled. Okay. So the scattering equations connected the space of kinematic invariance, where each point in the space of kinematic invariance, we decided to call it a matrix K with elements given by the Mandelstam invariance to the space of Riemann spheres with n marked points. Now, for every k, the scattering equations give n minus 3 factorial points in M0n, which is the name mathematicians give to this space. Okay? So, how do the scattering equations look like? Well, one way to represent them is as follows. Take this matrix and just make a minor modification to it. So, what we're going to do is that for every Mandelstam invariant that we have, we're going to dress it with the following factor, which I'm going to introduce here. Okay? So just to save a little bit of writing, every time you see a sigma with two indices means the differences of the two mark points. So maybe I should introduce a notation or remind you the notation for the mark points. They are denoted sigma 1 through sigma n, and this is all modulo SL to C. So what we do is that we dress every kinematic invariant with the corresponding propagator. Okay? Now you see that the way to get each of the terms in the matrix, in this matrix, is by just reminding that we are doing the inner product between K, 1 in this case, everywhere in the row will be a K1, dot the corresponding K that labels the column. So here it will be K2, K3, up to Kn. What do we have here? So we have S to 1 divided by S sigma to 1, 0, S to 3, sigma to 3, and so on. We'll also have a 0 here, 0 all the way here. And finally, we'll have S1n, sigma n1. Now this matrix will satisfy you more than the previous one, right? Because now this is anti-symmetric. So it has more right to have zeros in the diagonal. Okay? I know you were disappointed by the zeros here because the counting didn't feel natural for a symmetric matrix, but now this one is anti-symmetric. So let's call this matrix A. So this is not an amplitude, it's just the name I'm going to give to this m by m matrix. Okay? Now, the scattering equations are nothing but the requirement that this matrix A has a null eigenvector given by 1 in all entries. So if I multiply this matrix with this and I require that this be a null eigenvector of this matrix, I get the scattering equations, which are fairly easy to see, that they would be something of this form. Okay? By just doing the matrix multiplication. Now, let me call this EA. Yesterday, we also said that the space of mark points is only n-3 dimensional. So we would be in trouble if we found n independent equations. So we said that there were only n-3 independent equations. But I didn't prove it to you, and I'm not going to prove it today. But you're going to get an exercise because it's not that complicated. I'm going to tell you what the linear combinations are, and you're just supposed to prove that they actually work. So, of course, you're not going to assume that the equations are zero. So this is the definition of this object. Imposing that this is equal to 0 is a further condition, right? So right now, EA denotes this combination of objects. So the exercise is to show that these particular linear combinations of the scattering equations vanish if M takes any of these three values. Okay? Now that means, let's arrange these three values for M, or this vector of objects. Let's arrange them in a matrix that looks like this. And the reason I'm going to do this is that, well, then these linear combinations are just telling us that the vector of scattering equations annihilates any of these three vectors. But now there is something that we did yesterday that we could be forgiven for having done it because it was our first try, but it's something that is clearly wrong. So can anyone tell me what's wrong with this statement that we wrote down yesterday? We used that object inside a formula, and that was a complete disaster. We shouldn't have done it. Can you tell me why? You see, I'm imposing n delta functions, but three of them are linearly dependent. So on the support of the other n-3, three of these equations would be automatically 0. So three of the delta functions will be evaluated at 0 directly. So that would be a major disaster. So we shouldn't have done it. So what replaces this? So we better have something that only uses n-3 equations. But then if we do, it seems as if we are choosing particular values to leave out. So we had to choose 3 equations and leave them away. Somehow we should be able to do that while preserving permutation invariance. So it sounds impossible, but we're going to show that the following is true. So choose any 3 your favorite scattering equations, values. Let's call them A, B, and C, of course. And show that Well, I said, of course, but I shouldn't have said, of course. I mean, that's not a good name for the three values we're going to choose. Why is that? Because I always like to call the nth all the n particles with the index A as the label. So if I'm going to choose one particular thing, I shouldn't call it A. So let's use R, S, and T. Also not a good choice, because S and T are kinematic invariants, but hopefully you won't get confused, okay? So let's stick with R, S, and T. So I'm going to sum from A1 to N, but not including R, S, and T. Okay? So my goal is to find something that is independent of the choice that I made, okay? Well, what you do is that you start with this and try to compare it to something where you make a different choice and see if there is any factor that you can put in here to make it independent of the choice that you made. Now look at these metrics, and let me denote by R, S, and T the determinant of the submetrics made by taking the rth row, the s row, and the tth row together, and make a little determinant of the form okay? This is known as the van der Monde determinant of these variables. Well, it's not hard to see that this is just the product of these differences of sigmas. And my claim is that if you multiply this by R, S, and T here, let me remove the commas to save even more writing for you and for me. This is independent of the choice. So I'm putting an exclamation mark in case you're not surprised. You should be surprised. Say, wow. So that's... Yeah, so you try to change this. The way to prove it is to choose a different value for one of these equations that you remove, and then use the fact that they are linearly dependent, use the linear dependence to show precisely that this is the ratio of the two van der Monde determinants is precisely the price you pay for changing one equation by the other. Okay? Very good. So this is really what we should have used yesterday, and not this silly form of the delta functions. So let me denote this in order to just be fancy and claim that we were very, very close to this formula. Let's just put a prime here. So this prime means that we do this, okay? Now, there is also something else that I didn't tell you what to do with, which was the measure. So that looks very nice, but it's pretty much useless, right? If you want to do something, you have to do something that is explicit. Well, it's pretty standard. Anyone who has taken a string theory course knows that it's pretty standard how to compute the Fayet-Popov Jacobian of doing some gauge fixing. So if you choose any three values, they're not going to be A, B, and C. They're going to be, I don't know, P, Q, and R. No, R not. P, Q, and L. Okay? So if you choose these three sigmas to be the ones that you gauge fix, then of course you have to remove them from the integration. And quite nicely, the price you pay, or the Fayet-Popov Jacobian, is exactly the same as in this case. Okay? So yesterday, we spent a lot of time discussing this formula using the scattering equations, that the scattering equations being match the space of kinematic invariance with the space of marked points on the sphere, singularities map to singularities. So we got very excited, made a conjecture, but we actually haven't computed anything. So I thought that it would be a good idea to do a computation, which is usually a bad idea when you're giving a talk, but let's try. Precisely. The gauge fixing removes the volume factor, and this is all that is left. So now we have all the elements to actually do a calculation. So if you guys pay attention, I'm sure we're going to be able to go through the calculation without making a mistake. Because I'll make mistakes, so you will correct them. So what calculation do we want to do? Well, the simplest possible one we can make, which is a 4-point amplitude in the Bayer-Joint scalar theory. So let's do it. So we want to compute this amplitude in the Bayer-Joint scalar theory with the same ordering for both flavor factors. And the claim is that this object is nothing but the integral over the measure that we defined yesterday with this integrand. But now that we have all the elements to actually carry out the calculation, we should do it and see if the statement that I made yesterday actually holds. So, as we did yesterday, we selected only sigma 2 to be the variable that was going to be left, and 1, 3, and 4 were gauge fixed. I'm not going to impose the values now, I'm going to do it later, but I'm going to remember that only sigma 2 is the variable of integration that is left. And the way I'm going to remember that is that I have to put the Vandermonde determinant of the rest. So let me denote it like this, 1, 3, and 4. If you remember yesterday, we chose one of the 4 scattering equations to be the one we were going to solve. If you look in your notes, we made the choice of E1, the first of the 4 scattering equations. So I'm going to remove the other 3. By removing the other 3, I produce this Vandermonde determinant, and I get just the delta of the scattering equation E1. Together with the integrand all right. So next, we have to look at this explicitly, and this equation was S12 sigma 1 minus sigma 2 plus S13 sigma 1 minus sigma 3 plus S14 sigma 1 minus sigma 4 equal to 0, right? Now we are ready to do our gauge fixing. So setting one of the sigmas to infinity is always a scary thing to do. You're always worried that something will go wrong. But you also know that that choice is always a nice choice to make, because if you don't mess up, it's probably going to give you the simplest possible way of doing the calculation. So yesterday we chose sigma 1 to be 0, sigma 3 to be 1, and sigma 4 to be infinity. So the good thing about doing this is that we completely can forget about this term. So these scattering equations become S12, sigma 1 is 0, so we just get, also let me introduce Z so that it looks nicer. So we will look more professional doing the calculation. So this would be minus Z plus S13 divided by, now we get 0, and this is 1, so we get minus 1 in the denominator, and those are the scattering equations. Now let's try to write the whole thing. We're going to have the integral over z. The minus signs don't matter here. So we have, and I'm going to call this s, and this u, as you know very well, that's the convention that I like. So we're going to have s over z plus u. And the rest is going to be this combination of objects that I have to figure out how to evaluate. So let's start and do it here. So the first van der Monde determinant gives me sigma 1, 3, 3, 4, 4, 1. The second van der Monde determinant gives me sigma 2, 3, sigma 3, 4, sigma 4, 2. And in the denominator, we have sigma 1, 2 square, 2, 3 square, 3, 4 square, 4, 1 square. And now is the time to test that we didn't mess up by taking sigma 4 to infinity. We have 4 powers in the denominator, but we have 4 powers in the numerator. And you see that it completely cleans up the expression. So we don't care what sigma 4 is its friend in these combinations, because it doesn't matter. In the limit, all this goes away. And finally, we can get sigma 1, 3, 2, 3, sigma 1, 2 square, 2, 3 square, which very nicely, this factor cancels this. And that's what we have. And now let's write it in terms of the variables that we have over here. So 1, 3 is minus 1 divided by 1, 2 square times 2, 3. Is that correct? Maybe. Hopefully. Okay. I think so, right? Yeah, 3, 4. Okay. Let's keep going and hope for the best. So let's put here a 1. Let's put it outside. So now we have to get the value z from here. Well, if we do it, what happens is that we pull out the z. There will be a delta z. We have s plus u over z. Sorry, uz. We pull out the factor of u. Okay. And finally, we get 1 over this z squared. One factor cancels with this z. We get the factor of u, and we get z minus 1, evaluated at z equals 2 minus s over u. This doesn't look very encouraging, but let's keep going. Now let's plug this into the formula, and we get 1 over u. Here with this guy, we cancel the u, so we get s. This combination is just s with a minus sign. Now this combination would be minus s over u minus 1. And this thing is minus 1 over s. We pull out the factor of u that goes to the numerator. And then we get minus s minus u. But this thing is, no, don't tell me there is a mistake, because we just got the right answer. Now, you're not allowed to point out any mistakes, because this thing, this is t. Even the sign worked. So you don't have any questions, right? Which one? There is no minus sign. Look, the answer is perfect. Here we got it. Now we use that minus u is s plus t over s times t. And done. You see? Very easy. All right, so now you know how to calculate. So you can go on and do anything that you want You can go to 5 particles, 6 particles. All right, so after having fun with particles for the Bayesian scalar theory, we should go back to our business, right? Okay, before we go back to the business, yes. Yes. Yeah, you feel cheated now, right? It's like, darn it, what is the U? Yes. Yeah, the point is the following. Remember, we couldn't come out with an integrand that was permutation invariant. 1 over s plus 1 over t plus 1 over u is the amplitude in phi cube theory without any flavor structure. Yeah, so you could add the other 2 other terms square and divide by a factor in order to produce what you want. However, an interesting question is to ask, well, if this is the only thing that you could write as a first try, does this object have a physical interpretation in a particular theory? And the answer is yes, it's this amplitude. In the theory of a scalar, of a bunch of scalars that carry 2 adjoining indices and interact through the structure constants of un and um. So it's pretty good. So you wrote down something that you just made a wild guess, and it turns out to be computing something for which you can write a reasonable Lagrangian. So it's not that bad. Okay, very good. So now let's go back to our business, which was Yang-Mills. So we had a list of things that we wanted. We had a wish list. So let's do Yang-Mills. Now we have a single color group. And yesterday we made a conjecture that what we had to do was to keep the same measure. And in order to take care of this color group factor, we will be dealing with partial amplitudes, which are color order. So we have to make a choice of ordering, and that choice will be reflected in the factor that we're going to keep. From the 2 factors that we had for the Bayesian scalar theory. And then we made a conjecture that sounded cheap, which is, well, let's multiply this by a magic right integrand. And we call this one the left integrand. That had to satisfy tons of miraculous properties. Okay, but what was the very, very, very important property that it had to satisfy? Gauge invariance, right? Very good. So this amplitude will depend, for every particle, we will have a polarization vector and the momentum vector. The other requirement we're going to make on this, which I don't remember if we actually said it explicitly, is that this object should only be a polynomial in polarization vectors and momentum vectors. In other words, we don't want this object to have any poles in kinematic invariance. Why don't we want that? Yeah, it would be nice if it was ultra-local, right? But the philosophy of the whole thing is that the singularities should be generated by the modular space of the mark points, not by putting it by hand, right? So we didn't put the 1 over S and the 1 over T by hand in the exercise that we did before. They were generated through the scattering equations. So we should not be allowed to put this kinematic invariance in the denominator just because we're missing some and then we will sneak them in there, okay? So, yes? Why do we want it to be ultra-local? By ultra-local, I mean there is a polynomial, right? So why do we want it to be that? And then I just gave you the reason, which is not really a good reason, but it's a guiding principle, okay? Very good, so gauge invariance. So we said that this object should do the following. Right? So that's gauge invariance. So we should be able to shift the polarization vector by any longitudinal vector, and the answer should not change. Like, or equivalently, this object, if we make the substitution what should we get? Sorry? Yeah, so what should the answer be? 0. Very good. All right. So if this formalism is going to be any good, it better be that we make this as simple as possible, okay? So one criteria to make something as simple as possible is that it's a consequence of linear algebra. So if something happens to be a consequence of linear algebra, then I think it qualifies as being as simple as possible. So here I'm making a bunch of, I'm making up a lot of principles that don't make any sense, but it doesn't matter. So we've got these metrics. Wouldn't it be nice if we could expand these metrics in such a way that we could include the polarization vectors so that every time a polarization vector happens to like being a longitudinal vector, then the metrics would develop some linear relationship among columns and rows. If that was the case, then whatever object we construct, if we compute its determinant, it will be automatically gauge invariant as a consequence of linear algebra, which by my super fancy principle will qualify it as the simplest possible way you can make something to happen. Okay? So let's actually do it. How can we extend this to include polarization vectors? Well, there seems to be an obvious way to do it. We just erase this and keep going. And you now put epsilon 1, epsilon 2, all the way to epsilon n. And you do the same thing on the other side. Epsilon 1, epsilon 2, all the way to epsilon n. And now this is a big matrix, 2m by 2n. Well, actually, it helps to keep this division here just as a visual guideline. Now, if we did this for the momentum vectors, maybe we should do the same thing for the other ones, okay? So what entry should we put here? What would be your natural choice? Well, you see, k1 dot epsilon 1 is 0. So the natural choice will be 0. So k1 with epsilon 2 divided by sigma 1, 2, all the way to k1 dot epsilon n divided by sigma 1n. And here k2 dot epsilon 1 divided by sigma 2, 1. Here 0 again, all the way to k2 dot epsilon n, sigma 2n. And you keep going, you get to 0 here. Now on this side, you get 0 again, epsilon 1 dot k2, sigma 1, 2, all the way to epsilon 1 kn, sigma 1n. And here, the same thing, epsilon 2 dot k1, sigma 2, 1, and you keep going. And this is epsilon n, k1, sigma n1, and 0, 0. And now here with this, epsilon 1, epsilon 1. What should I put? I mean, it seems natural to also set it to 0. After all, we usually choose polarization vectors to be null. So we have this, and here we get epsilon 1, epsilon 2, sigma 1, 2, all the way to epsilon 1, epsilon n, sigma 1n, 0, epsilon 2, epsilon 1, divided by sigma 2, 1, all the way to 0. Okay? So now we are ready. We say, what happens to this matrix, which I'm going to call psi? What happens to this matrix if I replace, say, epsilon 1, the polarization vector 1, by its momentum vector? No, I haven't made any gauge choices. I've made a bunch of educated guesses, but I haven't committed to any gauge. All the polarization vectors are there. I haven't actually made any choices for them. No. That's a condition you have to impose. No, this is not a gauge choice. Yeah, don't confuse the two things. That's a transversal condition, right? So that has to be imposed. It's independent of the gauge choice. Yeah, thank you, yes. So in these formulas, SAB means KA.KB. Thank you, yes. I didn't want to change the notation, so yeah. Yeah, so in all these formulas here, in these metrics, we're going to take SAB to mean this. So everything is identical on everything. So it seems like the polarization vectors are behaving like a bunch of momentum vectors. Actually, it seems that there is no difference. So there seems to be even a symmetry between exchanging polarization vectors and momentum. Okay? This is? Yeah, this one is also anti-symmetric. Do you agree? Look at the matrix carefully. It is anti-symmetric, right? Look at this term and look at this term. It's epsilon 2 dot k1, and there is k1 dot epsilon 2. But this is a Lorentz inner product, so it's commutative. And sigma 2, 1 and sigma 1, 2. So this matrix is anti-symmetric. So what happens? So take the polarization vector 1 and replace it by K1. What happens? Yeah, look at this column. It becomes identical to this column by construction. And this row becomes identical to the first row. So actually imposing this, almost this symmetry between polarization vectors and momenta gave rise to a matrix that imposes gauge invariance trivially, according to my definition of trivially. Now, if we computed the determinant of the matrix, then gauge invariance would be manifest. I hope you all agree with me that this sounds too good to be true. In fact, it happens to be gauge invariant without even using the scattering equations. And if you remember in my conditions yesterday, I said that we wanted to impose the scattering equations. So the object should have been gauge invariant only on the support of the scattering equations. There is also another minor problem with this. The determinant of psi of this matrix, how many polarization vectors is going to have? How many copies of the polarization vector 1 is going to have? So here is a question. If you compute this explicitly, and you want to look and count how many powers of the polarization vector 1 have, what would be the answer? We get not only at least 2, we get exactly 2. So there are no terms without polarization vector 1. There are no terms with 1 polarization vector. And the way to prove it is by rescaling everywhere, by rescaling epsilon 1 by T1 epsilon 1. And you see that all this guy picks a factor of T1, and all this guy picks a factor of T1, and therefore the determinant is exactly proportional to T1 squared. And that means that there are 2 copies of this thing. And we don't want that, right? We want only 1 copy. Unless, of course, you were doing gravity. But we're not doing gravity, so we shouldn't get this. So this is bad. But the matrix is anti-symmetric. So I'm sure this is something that you also learned in high school, that if you compute the determinant of an anti-symmetric matrix, you do it for something that is 2 by 2 and you get this answer. You do it for something that is 4 by 4. And what do you get? Well, you get something that I wrote down yesterday, or the day before yesterday for a different reason. You get this combination of entries, all square. You say, wow, could that be true in general? Could it be that the determinant of an anti-symmetric matrix is a perfect square of a polynomial in the entries? And the answer is yes. And that motivated mathematicians to define something that is called the Pfaffian of a matrix that is anti-symmetric, happens to be, roughly speaking, the square root of the determinant. So there is a precise definition. But even better, in order not to give you the precise definition, I can define this like this, and it's exactly correct. Okay? So whatever is inside the square is called the Pfaffian of the matrix. So if you have something that has 2 powers of polarization vectors, in order to get just 1 power, all you have to do is to replace the determinant by the Pfaffian. So if you replace this determinant by the Pfaffian of the matrix psi, then we get exactly 1 copy this tensor is whatever is left, okay? That doesn't depend on epsilon 1. So don't worry too much about this tensor. It's just anything that comes from this calculation after you compute the Pfaffian, which is contracted with epsilon 1. This is just to show that it's multilinear in polarization vectors. So that sounds great. So we are doing great, right? So the object, but it's still trivially gauge invariant, yes. That's why I haven't erased trivially. This actually has a precise meaning. That is trivially gauge invariant. Okay, so but now we have come so far that it feels almost wrong to give up, right? So you have this object that does all these miraculous things, so it might be something. So why don't we compute an amplitude and compare it to what we were looking for and see if there is a problem, okay? So let's compute a very complicated 3-particle amplitude. Okay, so this is usually a good idea in when you're trying things. You start with the simplest possible case. So question mark, because we don't know. Let's do the 3-particle amplitude. So in the 3-particle amplitude, we started with 3 scattering equations, but we are supposed to remove 3 scattering equations. So there are no scattering equations. We only have 3 mark points, but we have SL2C, so we can fix all 3 points. So there is no integration. All we have are the Vandermondes of the particular variables, of the variables that we have. So we have 1, 2, and 3 square, one for the gauge fixing of the measure, and the other one for the scattering equations. Remember, we had 2 copies, but we only have 3 variables, so we have no choice. This is what we have. Times sigma 1, 2, 2, 3, 3, 1, which was our conjecture for the color factor, right? The term that is the left integrand that is supposed to take care of the color structure was just this. But this is exactly the definition of one of these guys. So it nicely cancels one of these powers. And now we are supposed to compute the Pfaffian of this matrix that is a 6x6 matrix. Well, that sounds like a very, very, very painful exercise. However, before we even start writing things, let's remember what happens for 3 particles. So for 3 particles, if you have K1 plus K2 squared, or also known as S12, modulo factor of 2, what do we get when we compute this for 3 particles? If you use momentum conservation, K1 plus K2 happens to be minus K3. But we're dealing with slip particles. So this thing is K3 squared, which happens to be 0. How about S23? Everything is 0. So this matrix is a big 0. So that's good news, right? Everything there is 0. Now that means that when we compute the Pfaffian, the only thing that will matter is this part. This part will not contribute to the Pfaffian. In fact, we end up with the Pfaffian. Yeah, we end up with the determinant of this, of that single term. Yes. So let's actually check what it is. So we have 0, epsilon 1, well, K1, epsilon 2, K1, epsilon 3. This one would be what? K2, epsilon 1. So here, let me put the bar to say that there are sigmas in the denominator. Okay? Well, whatever happens, when we compute the determinant of this matrix, we're going to get 3 terms. We're going to get the product of 3 terms, and they all look like this. I'm not going to bother to write explicitly what it is, because I hope you all know that this cannot possibly be Young-Mills. Why is that? Exactly. Remember that Young-Mills, our nice Lagrangian for Young-Mills, only has a cubic vertex of the form. So only 1 power of momenta is supposed to show up in the numerator. And we ended up with 3. So this is clearly wrong. Well, but still, could this be the amplitude of something? Well, maybe if you increase the number of f's, you would generate something that can give you something like that. In fact, if you do an f-cubed term, you can generate an amplitude that looks like that. But this is not what we're looking for. So we have to modify this structure. Now, this is a good opportunity to once again express the fact that sometimes you think that there is nothing that can be said new about a very old subject. But You'll be surprised sometimes. So, once again, but with different collaborators. And this was in 2016. They made two conjectures. One is the weak conjecture, not the weak gravity conjecture, but just the weak conjecture. And of course, if there is a weak, there has to be a strong conjecture. What's the conjecture? Well, let's start with the big one. The conjecture is, if you have any rational function that satisfies the following. It has poles consistent with trivalent graphs, with trivalent Feynman diagrams. In other words, you could start by writing all possible trivalent diagrams in phi cube theory and put numerators in there. Any numerators you want. Now, the claim is that if those numerators have n minus 2 powers of momenta and you impose gauge invariance, then your function is unique. And since we know that our amplitudes satisfy all three, then whatever function does this must be the amplitude. Then it's unique. Now you would think, well, what can be stronger than that? Well, the strong conjecture says that any function with the same two conditions here, but now any combination of poles of n minus 3 poles with these two conditions as well is unique. Why is this stronger than the other one? Well, for this condition, I'm assuming that you can have, say, for 5 particles. So let's give an example for 5 particles of the weak conjecture. You will write numerators. Very unfortunate that, well, there is an n and an n. But so these are numerators. And you're supposed to put here poles that are consistent with trivalent graphs. What's an example of a combination of poles that is not consistent with a trivalent graph? Well, let's give the example here. Again, for 5 particles. So the claim is that you can start even including, allowing things that look like this. Can everyone see? Well, first of all, can you see the indices back there? Yes? Very good. And can you see why this is inconsistent with a Feynman diagram? It's impossible to draw a Feynman diagram that gives these two propagators. Right? Because you need K1 plus K2 to flow into a vertex, but now that propagator carries K1 plus K2. You cannot separate 2 from 1 again. And if you put 3, you will just get the sum of K1 plus K2 plus K3, which is the same as K4 plus K5. So that should not be allowed in the weak conjecture. In the strong conjecture, you are allowed to do whatever you want. And the claim is that even relaxing that condition, the object will be unique. Now, what is our metrics getting wrong? On the power of polarization. No, the polarization vectors always have to be the object should always be multilinear in the polarization vectors. Yeah, okay, that goes literally without saying, because I didn't say. But yes, of course, the object is multilinear in the polarization vectors. Otherwise, we're not talking about gauge theory. But okay, so what is the thing that went wrong here? Well, as we said, we have 3 powers of momenta, and we were supposed to have only 1. So if we manage to reduce the number of powers of momenta, then we have a shot at getting something that will be unique, and therefore the right answer. So how do we do that? Somehow, this matrix has too many momenta in it. Exactly. So this object is what Arkani-Hamed and friends call trivially gauge invariant. So this object is trivially gauge invariant. In fact, you can show that by simple algebraic manipulations, you can write this as literally the product of 3 field strengths, which are gauge invariant, linearized field strengths. Very good. So now that we know the problem, that's half of the road to getting to the answer or to the solution. All right. So remember that our matrix A had 1 null eigenvector. In fact, I didn't tell you, but it has 2 null eigenvectors. Okay? The matrix A, by the scattering equations, this is actually tautologically, right? Because I define the scattering equations to be the equations that impose this to be true. But you could say, well, if you have the scattering equations, then you discover that the matrix A has this null eigenvector. But you would also discover that it has a second null eigenvector. The matrix A also annihilates this vector. And no, don't get excited, it doesn't annihilate the next one. Only these 2. Okay? Now, if that's the case, then maybe, in order to get a non-zero answer, if we were to compute the Pfaffian or the determinant of the matrix A, if we just do this right away, what do we get? We get 0, right? Because it has 2 null eigenvectors. Once again, if we want to make sense out of this in a way that is permutation invariant, something that we could do is to see whether we can remove 2 rows and 2 columns and compensate by a factor such that we get something that is permutation invariant once we compute the determinant of the reduced matrix. So let's take this matrix A and remove the ith and the jth row. And the K and the L column. Now we have an n-2 by n-2 matrix, and we can compute its determinant to get most likely nonsense, but whatever. We get something that is not 0, at the very least. The question is, can I put something here so that when I do this calculation, the answer is independent of the choice? But you saw that already. When we did it for the scattering equations, the linear algebra problem was the same. We have 3 null eigenvectors. And once you remove 3 scattering equations, all you had to do was to choose the Vandermonde of the 3 things that you removed. So in this case, This happens to be the answer. This object is what we could call the determinant prime of the matrix A, and is independent of the choice that I make of I, J, and K. Now, A was anti-symmetric, right? The original matrix. But after you remove rows and columns like crazy, the object is not anti-symmetric anymore, unless what? Unless you don't remove rows and columns in a completely arbitrary manner, but you remove the same two rows. Exactly, you make them equal to each other, and you see that the factor that it goes in front becomes a perfect square. So, choosing ij as a set to be the same as KL implies us that we can define this object. We can still compute the Pfaffian of this object, and this is independent of the choice. And this is something we're going to call the Pfaffian prime of the matrix A. Now you see that with this little exercise, yes? Try, it's not. When you compute the Jacobian that you have to compute for solving the scattering equations, the matrix elements are of this form. Square, yes. And that's why it has an extra eigenvector. In fact, isn't that nice? This matrix has one eigenvector, one null eigenvector. This matrix, so K, which is made out of SABs, has one null eigenvector. A, which is SAB divided by sigma AB, has two null eigenvectors. And the matrix, which people call phi, which is SAB divided by sigma AB squared, has three null eigenvectors. And this matrix is precisely the Jacobian of the scattering equations. When you evaluate the scattering equations, you are supposed to compute the determinant of that matrix. And the three rows and the three columns that you remove correspond to the three variables that you remove and the three equations that you remove. Okay. Well, but why did I do all this? Look at this object now. How many powers of momenta does it have? We have reduced the number of powers of momenta by 2. Exactly by 2. So if we were able to do the same thing to the big matrix, we could define a way of removing 2 rows and 2 columns of the first block of n columns and the first block of n rows, then the resulting answer will have exactly n minus 2 powers of momenta, and it will be gauge invariant. That would be very, very nice. But in order to do that, we know the trick now. We have to generate, in whatever way we can, 2 null eigenvectors. Okay, so I'm not going to be very ambitious. I'm going to try to make this a null eigenvector of the matrix. Okay? Well, clearly, when I multiply this part with this part, I get 0. This with this, I'm cheating, right? Because now it doesn't see it. It seems very good. So I keep going, I get 0, 0, 0. So everything is going great. Just when you think that you're done, you get to hit this part, and you go here, you hit it with this thing, and you get something here, which is just a mess. So it's the sum epsilon1.ka over sigma 1a from A2 to n. says, if I could only make this 0, everything would work, right? And here, you get the same thing, but now with epsilon2.ka, sigma 2a, a different from 2, and so on. Say, well, maybe I can modify my metrics in order to get these things to work. But where would you mess with these metrics? Well, what were the only places where we made a choice that wasn't completely natural? When we set these diagonals to 0, we made a choice that was just arbitrary. So maybe this is a place where we can allow ourselves to do something. So let's call this C11, C22, all the way to CNN. Of course, we don't want to mess with the fact that it's anti-symmetric. So we need this one to be, whatever C11 is, this will be minus C11, minus C22, all the way to minus CNN. And now we can tune this to fix our problem. Because now when we do this column dotted with this guy, we get this, sure, minus C11, because the first guy is a 1. And now we impose this to be 0, and it seems to work. Okay, but making this have a 0 eigenvalue, a 0 eigenvector, maybe it wasn't that difficult. After all, we can solve for these guys linearly to make this happen. What do we have to check now? What's the very, very, very important property that maybe we completely destroyed by doing this? Exactly, gauge invariance. So let's remove this. And say that CAA is equal to the sum over epsilon A dot KB AB for B different from A. So let's check gauge invariance before we continue, because otherwise we're wasting our time. So you always have to go back and check something fundamental before you continue, because if we destroy this, then there is no sense in which we can continue. Okay, so our test of fire was to replace the polarization vector 1 by K1, right? And we had to develop a linear dependence. Now we know that everything should work in the same way as before, except the new part, okay? Where something else could happen. But let's have a look at C11. So C11 is the sum over epsilon 1 dot KB divided by sigma 1b, b from 2 to n. And when we replace epsilon 1 by K1, what happens? Well, let's do it. And what is this? Generically, it's not 0, but on the support of the scattering equations, this happens to be exactly the scattering equation. So this object is gauge invariant only on the support of the scattering equation. And it's trivially, well, it's easily gauge, no, I shouldn't say trivially. Trivially, we gave a technical definition according to our friends over there. So this one is very easily gauge invariant, but only on the support of the scattering equations. And this exactly does what we want. So let's now complete the story by giving you the exercise of showing that not only the vector 1, 1, 1, 0, 0, 0 is a null eigenvector of this object, but also the one sigma 1, sigma 2, sigma n, and then 0, 0, 0 is also a null eigenvector of this matrix on the support of the scattering equations. And therefore, everything we did here can be done for the matrix psi. Of the matrix, okay? So those are the only ones that do special things. So I and j are restricted to be in the first, well, there is no zero. From the first set, and this object is what is called the Pfaffian prime of the matrix psi. And if the conjecture of our friends is correct, then we have succeeded in computing the scattering amplitude, the full S matrix, three-level S matrix of Young-Mills in any number of dimensions, because we haven't imposed any condition on dimensions. So let's write our answer. The partial amplitude with ordering 1 to n is given by the integral with a special measure of the left integrand, sigma 1, 2, 2, 3, all the way to sigma n1, times the Pfaffian prime of psi. Okay? And we even have 7 minutes to spare. I mean, this is pretty good. So what do we do now? So we have this formula. Now we recollect the formulas we have and see if we can learn something from them. So this is a formula for Young-Mills. Let's collect the formula now on the same board for the Bio-Joint scalar with ordering 1 to 2n, and then some other ordering, omega 1, omega n. This formula is the integral over the same measure of the same factor times another factor, but now with this new ordering. Now, given these two formulas written like that, and what we talked about during the first lecture, it's very tempting to complete this. It's like it's missing one equation at the bottom. What could it be then? So here, if we start with this formula and replace this kinematic factor by a copy of this color factor, we got the Bio-Joint scalar. The natural thing to do now is to replace this color factor by another copy of this object. Now, the polarization vectors don't even have to be the same. We can choose them to be different. And this formula, then, exactly, it better be capital M. All right. Sorry? Yes, this is Einstein gravity. Well, you saw how by messing around with the formula, we ended up with something that computes something that looks like f cubed. So you could try to change this formula to produce things that correspond to r cubed terms. In fact, people have done it, so you can look at papers by Song He, where they have developed formulas for computing higher derivative corrections. Okay? Well, but given that we have 4 more minutes, we don't have to stop here. Why not? Because is there any other formula on the board that you think we could use as an integrand? So remember that the only conditions, or the most, well, not the only, but the most basic condition that we imposed on the total integrand was the transformation under SL to C, because we had to eat up the weight of the measure. And we started by dividing this into 2, and we said that each piece had to transform under SL to C like this. And do you remember the power? For just a half integrand, it was square. And I said that, well, maybe, even that this is square, there seemed to be a chance of introducing a quarter of an integrand, meaning a new object, let's call it left 1, that will transform in the same way as this, but now with a single power. So that we can start playing around and construct integrands that are split into 4 pieces. And then check if they correspond to any theories that we know. In fact, that was a game for a long time. You would just come out with a formula, compute the S metrics, and then go around asking people, have you ever seen anything that produces these amplitudes? Have you ever seen something that... So in my experience, the people you want to go and ask are the people who do particle phenomenology. So they were the ones that were the most useful in recognizing these S matrices. So let's see. Once again, is there something that we can use that we have on the board that seems to be a nice object or a candidate to be used as a quarter integrand? Well, look at this. How about this object? Or even better, the Pfaffian prime of A, because A is anti-symmetric. So we could also define the Pfaffian prime of A. How do you think this guy transforms? As a quarter integral, half integral, integrand, sorry. Yeah, this guy transforms as a quarter integrand. So this one can be used. Maybe I should actually introduce notation like this. It's a quarter integrand. And this guy could be used as a full half integrand. And you could even put 2 powers of this guy and then get a total integrand. And then here is where the game begins, because we can do exactly what we did there and start with this line, keeping it the same. And in the next line, we write this object and put here what is going to be a half integrand. And then keep going and write this. So you start with these objects, You compute many examples, as many as you can, and you start asking around. It turns out that this, when you compute it, we started to ask around with the S matrix elements, and nobody could tell us what they were. So we decided to construct a Lagrangian that would produce this S matrix, order by order, and see if we could resum it and get something. Now, the hint is that this is a scalar theory, right? It's a scalar theory with many derivatives, because the matrix A has tons of derivatives. So a scalar theory with derivatives. Remember, this guy was a scalar theory with no derivatives, the bi-adjoint scalar. This guy will have derivatives, and it has two color structures. Sorry, this one has only one color structure, and it ended up being something like this. So we have a matrix phi. Now this is the color index, and I'm only going to take one more minute. So we sum over A. Let me note it like this. And the Lagrangian that you get is something that looks like this. I'm going to introduce a coupling constant because, well, there has to be some coupling constant. And then we went around checking with people. Have you ever seen a Lagrangian like this? Have you ever seen? Until finally somebody said, yes. This is nothing but the Cayley representation of a very famous Lagrangian, which is the leading order in the chiral Lagrangian. So there is a field redefinition so that this Lagrangian can be written as the trace where U is e to the I, dA, and this phi is a different phi, so maybe I could call it chi A, with some coupling constant that is usually called F. And this is a theory that Shiraz was talking about. This is the nonlinear sigma model, and it's useful in the description of pions. We usually take these matrices to be 2 by 2, and this describes pi plus, pi minus, and pi 0. But then how about this one? Well, this one turns out to be a theory that is even more exotic and that started to appear not long ago in the study of models where you introduce, well, you do something to gravity you don't want to know, so I'm not going to tell you, okay? But in any case, you do something to gravity, and in the end, you end up with an effective field theory with the scalars with an incredibly large number of derivative interactions. And somehow, that's what this formula is computing. Why is that true? Still not completely, it's not completely clear. But tomorrow, we're going to give some hints of why these theories are special, okay? So I'll stop here. Well, it's exactly the same. These are the partial amplitudes. So we still haven't committed to any group, right? The color factors are the traces that we are not writing, right? So then it could be UN for any n. Yes? Yes? Yes. Yes. It's hard to tell. So you'll have, it depends on exactly what is the thing that you're putting in. So people are exploring all these possibilities. Yes. Sorry, can you say? Oh, you mean if I put here determinant of psi and Fabian prime of psi? Well, determinant of psi has the weight of a total integrand. So I would violate the SL to C. Yeah, you could try to put one of these factors in the numerator now to compensate it. But it turns out that when you do these things, every time you try something, and you're welcome to try, but you end up with a theory that doesn't make quite sense. Yes. Yeah, so why are the null vectors important? The reason is that, you see, they are the ones that allow me to define this object, which is permutation invariant, and has 2 powers less of momenta than the original object. Yes, but it wouldn't be permutation invariant. Yes. Sorry? Well, if you allow a fractional power of the Pfaffian, you get a fractional power of polarization vectors. Now you tell me. What would you do with the square root of epsilon of the polarization vector? That would be a very strange wave function for your particle. Yeah, sorry. Oh, yes. This guy is a scalar field. It's not the same as that scalar field, because you need a field redefinition to go from here to there. Oh, this is a mu, dagger. Oh, here. The pion coupling constant. I mean, people usually denote it as F. I don't know why capital F, but it's just, in case you have seen it, you can make the connection. Yes. Or maybe 1 over F, so I cannot guarantee it. Yes. Well, the way I'm using the conjecture is just to tell you this object, whatever it is a rational function of momenta that has poles precisely where trivalent graphs have poles. And they are consistent with trivalent graphs, okay? So I can even use the weak form of the conjecture. And the power of momenta is m minus 2 because I put the prime, and it's gauge invariant. So if the conjecture is true, then I don't have to do anything else. This is a proof that I cannot tell you exactly what is known, and I'll have to double check. But just look at the paper, check the citations, and then see how progress is going. I haven't used quarter integrants yet. Yes, that's true. And the reason is that it seems I haven't introduced anything else that can be by itself combined, right? But let me give you an example of another quarter integrand. And you can, as an exercise today, you can have fun putting everything together and see what you get. So here is another quarter integrand that you can use. It's 1 over the product of sigma I and j, where I and j belong to a perfect matching of the graph with n vertices. The complete graph with n vertices. With n, yeah, no, it's vertices, yes. So what is a perfect matching? Well, just think that there is a room with n people. Of course, n has to be even, otherwise there wouldn't be any perfect matching. And then you ask people to pair up. Okay, so you call I and j. So here in the graph, you denote every pair. So 1 and 2 are pairs, so you have to remove them from the graph. They are not allowed to be used again. So 3 with somebody else here, n with somebody else here. So any choice of perfect matching would give rise to a quarter integrand. Yes? just 1 second, just to say, then you can use that quarter integrand times the Pfaffian prime of A to make a half integrand, and then put it together, say, with this. And now it's your exercise to find what theory that computes. Yes, sorry. Yes. Somehow these models are related to these string theories where you treat very differently the left and the right movers, where you impose different vacuum conditions for both of them, and somehow that removes it changes the bar of one of the halves and makes the whole model holomorphic. Yeah, but what? Well, the natural thing to try would be to change the scattering equations for something else that now depends on Z and Z bar, right? Then you would say, well, I have to put something that depends on Z and Z bar for ZA and ZB, right? Now this would be ZA minus ZB. So I need something that has these things in there. Well, you say, well, now, but what do? I want to integrate over things and have something like this, but I need kinematic invariance. So where do I put them? Well, this is the only natural place. And guess what you get? But you get a string theory amplitude. Yes. And that factor there is called the Koba-Nielsen factor. I know this. All right. Okay, thank you.